Hello, Mr. Colati here, and today we are going to learn the remaining trig identities that we are going to need for this course. So far you've learned, or we've talked about, sine squared plus cos squared equals 1, and we've talked about sine over cos equals tan. Today we're going to learn the two double angle identities. Double angle identities, a little bit of a tricky concept. But let's start by talking about what is a double angle. Well, technically, this is an angle. Let's say this is 30 degrees. A double angle is if I double the size of it. So now it becomes an angle of 60 degrees. So I've taken that angle, I've multiplied it by 2. You say, oh, Mr. Colati thinks this is difficult. Well, it does get a little tricky because this is a situation where the math doesn't behave as intuitively as we think it will. For example, if I have theta, 15, 30, and 35, what's sine of those values? Well, let me just do that with my calculator here. So I have sine 15, that would be 0.259. Sine 30 is equal to 0.5, of course, and sine 45 is equal to 0.707. Okay, so you might be thinking like, okay, well, if I want to take the sine of the double angle, so that would be 30 degrees, 60 degrees, and 90 degrees. Well, you kind of might be wondering, or the thing we're going to try to answer, is sine of the double angle equal to 2 sine theta? In other words, can I just pull the 2 out, like kind of factor it out, or kind of like I do in other math situations? Well, let's see. So 2 times sine theta is 2 times these numbers. So this would be 1.414, 0.5 times 2, well that's 1, obviously. And 0.259 times 2, that gives me 0.518. Okay, is that the same as if I had just said sine of the double angle? Sine of 30 is 0.5. Sine of 60 is 0.866. And sine of 90, we should know that's just 1. So through this kind of little investigation, you can see that this intuitive idea is not applicable, right? And so just make sure that this is not true. Like, no, don't. We find that sine of 2 times theta, you can imagine this in brackets, does not equal 2 times sine theta. So again, the math is a little weird here, or it's not intuitive. You can't just factor the 2 out. And that's why you're going to find that this can be a little bit challenging. Similarly, cos 2 theta, that does not equal, if I did the same activity, that does not equal 2 cos theta. Formally, the double angle identities, like the way that I can find sine 2 theta is with this identity, this formula. Sine 2 theta is actually equal to 2 sine theta cos theta. And cos 2 theta, there's a few different options here. 2 cos squared theta minus 1, 1 minus 2 sine theta, and cos squared theta minus sine squared theta. These are my double angle identities. So it's not enough to just look at this sine 2 theta and say, oh, that's 2 sine theta. It's not that. Sine 2 theta is 2 times sine theta times cos theta. And you have a cos 1 over here. Now you might be saying, where did these come from, Mr. Colati? What's the deal? Well, I have a proof here that I've kind of laid out for you. You're not expected to understand this or reproduce it, but if you want, you can go through and read it. I mean, basically, we've drawn this triangle here. It's a right angle triangle. I've divided it up into 2 isosceles triangles, two right angle triangles that are congruent, that are the same. I've used my trig ratios to define the different lengths. So for example, Pn, I defined in terms of the double angle. This is a double angle, and these are the single angles. This layout ensures that. I kind of proved it here. By similar triangles, I know that this length, an to np, is the same as am to ao. Those are similar triangles. The angles are the same, right? This angle is the same. So I sub in my values that I found here, and through a bunch of mathematics, I arrive at these different double angle formulas and the sine double angle formula, double angle identity. Anyways, you can digest that if you will. I know at this point in the course, the last thing you want to do is go through another identity, right, or another proof. You're at the end of your rope with IB, so we're going to keep going. So let's give these new identities a spin. So for example, if theta is equal to 30 degrees, then the double identity would be, or the double angle would be 2 times theta, which would be 60 degrees. If I want to know what sine 60 degrees is, it would be 2 times sine 30 times cos 30. Using my special triangle, sine 30, if you can imagine that special triangle, it is 1 over 2. Cos 30 is, if you can imagine that special triangle, root 3 over 2. So I end up with root 3 over 2, because those 2's cancel out. Neat. Seems like a circular logic thing, and because you never really would go through a process like this necessarily, but let's turn the page and we'll see some practical situations with this. Okay, given sine 15 is equal to this, find cos 30. So here's an example of a question I could give you where you would have to figure out, where you'd have to use the double angle identity. So we know that, I mean, you can look in the question too, like there's an angle, there's double the angle. This makes me think that this is a double angle identity. Theta is equal to 15, 2 theta is equal to 30. So if I want to find cos 30, well, I'm going to use my double angle identity. Which one though should I use? Oh, maybe I should write this as, let me write this as cos 2 theta. Okay, oops, that doesn't look so nice, but let's use, which identity do we use? Well, I know what sine is. So if I go back to my cos double angle formulas, I'm not going to use this one because I don't know what cos 15 is. I know what sine 15 is. So I'm going to use 1 minus 2 sine squared theta. So now I can sub in the values. So it's cos of 2 times theta. So cos of 30 degrees is equal to 1 minus 2 sine squared of 15 degrees. You can sub in your numbers. So sine 15 is 0.2588 squared. And that's going to give you an answer of 1 minus 2 times 0.2588 squared. 0.866. Neat. So where we're going to find that these identities are more useful is solving equations. Or maybe not more useful, more painful, solving equations. Part of the difficulty is knowing when you need to use a double angle formula or double angle identity. I'm always going to say the wrong thing. So let's look at this next question. I've been given sine theta is equal to something. So this is a non-calculator question. And I want to know what sine 2 theta is. Well, that's good. Like, this is very clear to me that this is a double angle. So immediately I should be thinking about my double angle identities. All those identities are on your formula sheet, by the way. So sine 2 theta is equal to 2 sine theta cos theta. Well, this is good news. I'm almost there. All I need to do is sub in my values. And I know what sine theta is. Oh, but I don't know what cos theta is. To find cos theta, we use another trig identity. That trig identity is the Pythagorean identity. Sine squared theta plus cos squared theta is equal to 1. Watch how this works. I can use, okay, so sine theta squared is 5 over 13 squared plus cos squared theta is equal to 1. Now, if I solve this equation, it's going to be 1 minus 5 over 13 squared, which is 1 minus 25 over 13 times 13 is 169. So I end up with 169 minus 25 over 169, because I made this 169 over 169, so I had a common denominator. And that gives me, what's 169 minus 25? 164, 144 over 169. Now, if I want to find out what cos theta is, well, that would be the square root, right? The square root of 144 over 169, which, oh, plus or minus the square root, sorry. So that gives me positive 12 over 13, and cos theta equals negative 12 over 13. So I have two answers here. Oh, wait a second. Theta, the angle theta, has to be between 90 degrees and 180 degrees. Now, if you can imagine that for a minute, where should I write this? I guess we'll write it right here and make a horrible mess, but so cos, if we're talking about this quadrant, we're talking about this quadrant here, so CAST. We're talking about some angle in this quadrant between 90 and 180. Well, cos is clearly negative. When theta is between 90 or pi by 2 and pi. So therefore we wouldn't use the positive one, it would have to be this one. So that's our reasoning right there. So now I know what cos theta is, I know what sine theta is, now I can finally use this, all this blank space I have over here, and put my values in. And I get to 5 times 12, 60, so I have negative 120 over 169. That's my answer. What a whirlwind that was. Sorry about the poor space allocation. You might be wondering, what was theta? Right? What was theta? And the answer is, we shall never know. But we figured out what sine 2 theta is. Here's another question that we can do. This one is a trig equation. So find the exact solution of sine 2x plus sine x equals 0. I did put some hints down here for using double angle identities, because again, one of the most difficult parts of double angle identities is knowing when you have to use them, because they're hard. They're harder to use. But here, so what I said is, if you're given the exact value for a trig ratio for an angle that is half or double the angle given in the question. For example, if you're asked to, if you're given sine 50 and asked to find sine 100, like that question we just did, right? You were given sine theta, you were asked to find an angle that's double. So it was pretty clear what you had to do. The other situation would be if you are solving an equation where the trig ratio angles are different. For example, solve the equation cos squared x equals cos 2x. And that's what we have in this situation. So the big giveaway here, that it's not quadratic, it's not some other trick, it's that this angle is double this angle. It doesn't matter which one's double which, it's the fact that you have a question that has both, an angle and then double. This should indicate to you that something's going to happen where I have to use a double angle identity. Remember in what our lesson from yesterday, we wanted to solve a trig equation. We want to get it so it's sine x equals something. So I want to try to combine these two. I want to try to turn them into the same, add apples and apples instead of apples and oranges. So what I'm going to do is I'm going to use my double angle identity to rewrite sine 2x. I'm going to write this as 2 sine x cos x plus sine x equals 0. So I use my double angle identity. Okay, and now, well, I guess I can factor this. So I'm going to factor out the sine x. And that's going to leave me with 2 cos x plus 1 equals 0. So that there is I factored. And now, look at what you have. You have an equation that's been factored. So for this to be true, either the first factor has to be equal to 0. Sine x is equal to 0. When does this happen? Well, you could use your unit circle. I tend to prefer to solve a question like this. I know this is either 0, 90, 180. I always get confused. The best way I find to do this is to just think of the sketch of the curve sine x, right? This is y equals sine x. Where is sine x equal to 0? Well, here, here, and here. That's how I tend to remember this. So then I know that it's equal to 0 at x is equal to 0. Oh, sorry. This is true at x equals 0, x equals pi, and x equals 2 pi. Now, there's also a possibility here, right? This would be if 2 cos x plus 1 is equal to 0. So I'm going to bring the 1 to the other side. I'm going to divide both sides by 2. So when is cos x equal to negative half? Oh, this is where I have to do that thing with the cast rule again. So I have to find the related angle, or I have to think about what's the related angle. To do that, okay, when do you have a 1 and 2? Which special triangle is that? Oh, it's this one. This is pi by 3, pi by 6, 1, 2, root 3. Make sure you draw it correctly. So the related angle when I have half would be adjacent. So it'd be 1 over 2. So it'd be the related angle is pi by 3. So now you can go to your cast rule. Well, I don't know why I'm making this so small when we have so much space here. When is cos going to be negative? Well, it will be negative in this quadrant and in this quadrant, right? And this, so I have either this angle, which would have to be, if this is pi by 3, this would have to be 2 pi by 3. And if it was this circle here, it would be 4 pi by 3. So that would be x is equal to 2 pi by 3 and x is equal to 4 pi by 3. Are all of those answers acceptable? Well, they all have to be between 0 and 2 pi. So one of those, yeah, 0 and 2 pi and 0 and 2 pi. So those are the 5 angles that make this statement true. So again, what did we do? We used the double angle identity to get into a situation that I can then factor and solve each factor. This got a little messy because I had to find the related angle, and I tried to draw it really, really small to make it hard on your eyes. Okay, so now your homework for this section. And this section really does merit its own kind of homework area in the book, because you're going to find that the equations, the trig equations, can get really confusing really quickly. So we have page 460, number 1 to 7, and we have page 461, number 2. Good luck with that, and we'll see you next time.